looking into the pop instruction. So, this is just the reverse of push. So, in case of push instruction, so we are saving the content of this register pair onto the stack. So, this pop instruction is to retrieve the register pair value from the stack. Again, the pop works with register pair, not with the single register. So, the way it operates is that it copies the content of memory location pointed to by the stack pointer to the E register, then increment the stack pointer, and then it will be copying the content of this stack point memory location pointed to by stack pointer into the D register, and then increment the stack pointer again. So, if we think if this is the sorry. So, if we look into this one, so if this suppose this is the stack, this is the portion of the stack that we have, this is the memory location and this is the stack. So, stack pointer is now pointing to this place. Now, when we do a pop D, then so this location's content, so this location's content is first copied onto the E register. So, this is the D pair. So, this content will come to the E register and then the stack pointer will be incremented. So, stack pointer now points to this location, the next location, and that location's content will be copied onto D register. So, whatever be the content here will be copied onto the D register, and then the stack pointer will be incremented further, so that it points to the next memory location. So, that way this pop instruction is executed. So, it is just the reverse of push. So, this push pop instructions can be useful for saving some value temporarily into the memory. So, now how this stack is used? So, during pushing, the stack operates in a decrement then store style. So, first as if you look into the instructions, then you see that here it for the push instruction. So, it is decrement SP and then do the copy, then again decrement. So, it is first decrement and then copy, whereas for pop it is first copy then increment. So, you can say that during push operation the stack operates in a decrement then store style. The stack pointer is decremented first and then the information is placed onto the stack, and for popping the stack operates as use then increment. So, as if it is all the copy then increment style. The instruction is retrieved from the top of the stack and then the pointer is incremented, and stack pointer always points to the top of the stack. So, that is by the definition of this stack data structure, that it always points to the top of the stack. So, that is taken care of in the 8085 stack operation also. Stack works in a LIFO fashion, last in first out fashion, because the basic 8085 designers, so they have not put any restriction like the order in which you do a push pop operation, but as a user of the system, so we have to be careful. So, the order of push and pop, they must be opposite of each other in order to retrieve information back into its original location. So, maybe I have got a piece of program, and that in that so we do not want that wherever from wherever place I have called this program. So, whatever register this program uses. So, let us say that this uses the registers B, C, D and B, C, D. So, these register pairs it is using. Then what I want is that wherever be the program from where this one has been called, so after this program has finished, so the B, C, D, E register, they should get their old values back. So, we will see later that this type of situation occurs when we consider the interrupts in a system. So, what we want is before coming to this routine, whatever be the values of B, C, D, E, after finishing the routine, the values should be restored to those. So, for that purpose, we have to save this register. So, we should have two instructions here, the push B and push D. So, these two instructions should be there for putting it for saving them onto the stack. Now, at the end, what is required is that we have to retrieve the content of these four registers B, C, D, E. And how do we do that? How do we do that is by means of this pop instructions, and this popping has to be done in the reverse direction. So, that is pop D and pop B. So, if we do not do that, so if we by mistake, so if we write as first pop B and then pop D, then the content will be reversed, isn't it? Because in the stack we have saved this B register first and then the D register. So, while popping out, so I should pop out D register first, then the B register. So, the order in which you have pushed into the stack, so while popping out you should do it in the reverse order. So, that is why it is called a last in first out structure or LIFO structure. Another very interesting register that this 8085 has is the PSW register pair. So, this is PSW physically the register consists of the accumulator and the status word register. Okay. So, this is called program status word or processor status word sometimes. So, this register pair is made up of the accumulator and the flags register. So, this accumulator and flag, they constitute this PSW register. It is possible to push the PSW onto the stack, do whatever operations are needed and then pop it off the stack. So, that way we can use this PSW register. The result is that the content of the accumulator and status of the flags are returned to what they were before the operations were executed. Again the same thing, many times we want that this A register and the status, they should be available at the end of the program, at the end of the execution of a piece of program. So, for that purpose at the beginning you can do a push PSW instruction. So, you can have an instruction like push PSW at the beginning, and at the end, so you can have pop PSW. So, you can have push PSW and pop PSW as the two instructions. So, that is the utility of this PSW register pair. Next, we will be looking into one very important concept which is known as subroutine. So, a subroutine, it is a group of instructions that will be used repeatedly in different locations of a program. So, rather than the same instructions putting same instructions several times, they can be grouped into a subroutine, and that is called from the different locations. So, this is similar to the procedures that we have or the functions that we have in higher level languages. So, here we write in case of assembly language program, some part has to be repeated. So, we just put it separately, and then we can just call this subroutine. So, if I have a piece of program, and if we find that in that program, so these some parts of the program are similar, only some parameters, some registers are changing and things like that. Then what you can do, so if this code and this code are very similar, so you can reorganize this entire code like this. So, you put a small portion at the end. So, that is actually the code that we have here. So, since the codes are similar, so we put the code only once, and so this will be called a subroutine, and this subroutine is called from different places. So, at this place we have got a call. So, this is a call to the subroutine, and similarly sometime later again you give a call to the subroutine. So, this is a call to the subroutine. So, this way what we are saving is, we are saving the extra program length that we had. So, because of this is only twice that I have shown here. So, maybe one routine is needed very often. So, as a result, so it is called several times, it is copied several times in a straight line code. So, if you are putting a subroutine, then that part can be saved and we can make the program size small, particularly in microprocessor based systems. So, since the space is a concern, so making them small saves the space. So, that is the utility of this subroutine. So, rather than repeating the same instruction several times, so they are grouped together into one subroutine and they are called from several locations. In assembly language, a subroutine can exist anywhere in the code. So, though in my example I have shown the subroutine to be at the end, but it is not necessary. So, you can put the subroutine at any place. So, it does not put any restriction in assembly language programs. So, there is no restriction, but for the readability purpose, so they should be put separately from the main program. Otherwise, readability becomes a problem. Next, in case of 8085, there are two instructions that deal with subroutines. The call instruction, that is used to redirect the program execution to the subroutine, and the return instruction or RET instruction used to return from the execution to the calling routine. So, for example, this call 4000 hex, so that will be used, that is for calling the subroutine, and we have got a return instruction. So, it is like this, that if this is my main program, and then so suppose your main program starts at memory location 1000 and it goes like this, and then this is the subroutine that you have at starting at location 4000. Now, somewhere here at location say 2000, I want to give a call to this subroutine. So, for that purpose the instruction is call, this is the call 4000 hex. So, the size of this instruction is 3 bytes. As you can understand that call will take 1 byte and this 4000 hex will take 2 bytes. So, total is a 3 byte instruction. So, location 2000, 2001 and 2002. So, they are holding the instruction, and then when this instruction is executed, what the system does, it jumps to the location 4000 and starts executing from this point onwards. Now, any subroutine, it should end with a return instruction or RET. So, when the processor finds this RET instruction, okay, so RET is again one byte instruction because it has only the opcode part. So, when this RET is found, then the processor will try to come back to the location just after the call instruction, that is the 4002. Okay. So, it will 4003. So, 4000, 4001 and 4002, they were the call instructions. So, when this return is executed, it will try to come back to 4003. Now, the question is how does it come back? So, how the processor will know, in the return address I am not mentioning like where to go. So, how the processor will know where to go? So, this is actually accomplished by the call mechanism. So, at the time of calling itself, so this is taken care of, that we have got this return address saved onto the stack. So, in this call instruction, so push the address of the instruction immediately following the call into the stack. And as I have said that call is a 3 byte instruction, so the immediate next instruction is at address 4003. So, this 4003 value will be pushed onto the stack, and then so what happens is that, so if this is the stack, so value 4003 will be pushed onto the stack, and as we know that it is a 40 is the higher order byte and 03 is the lower order byte. So, this is the, so stack pointer will now point to this location. Okay. Now, it will be calling, it will now the program counter value, program counter register will be loaded with the 4000 hex. As a result, from the next instruction, the processor will execute from location 4000 hex. So, after some time, so it will be finding the return instruction, and then it will be popping out the content from the stack to get the return address. So, we will see how is it done. The return instruction, so it will retrieve the return address from the top of the stack. So, it will get the content from the top of the stack and it will load the program counter with the return address. And as we know that the program counter register, it actually determines the instruction which will be executed next. So, for the return, what we need to do is to get the content from the stack and put it onto the program counter. So, that is exactly what is done in the return instruction. So, there can be some caution, like the call instruction places the return address at the two memory locations immediately before where the stack pointer is pointing. So, you must stack pointer correctly before using the call instruction. So, this is, so 8085 designers what they have done. So, they have made the say call instruction execution like this, that this program counter value will be saved onto the stack. Now, if so, but it does not do anything regarding the stack pointer initialization. So, if by mistake the stack pointer contains some garbage value, then the program counter values will be saved onto that memory location. So, that makes it very difficult, like, so it is the user's responsibility to ensure that the stack pointer is pointing to a valid memory address from where which is not used for any other purpose, and the return address can really be saved onto that address and can be retrieved later. So, before the call instruction is call instruction is put into a code. So, before the first call instruction, if this is my program, somewhere I am doing say call to some address. So, before doing this call, somewhere previously I must have executed this instruction LXI SP comma some valid address, so that the stack bottom is loaded onto the stack pointer. Stack pointer points to the bottom of the stack. That should happen, and after that only this call should be executed. So, this is just a precaution. So, if you do not do this, if you do not execute the LXI instruction, then also this call will execute, but the effect may be disastrous. So, this may be that it corrupts some other values of your program, other data of your program, because the stack pointer points to those arbitrary locations, and then it tries to write this program counter value there. So, you must set the stack pointer correctly before using the call instruction. Similarly, the return instruction, it takes the contents of two memory locations at the top of the stack and uses these as the return address. So, we should not modify the stack pointer in a subroutine. So, if in a subroutine, if we modify the stack pointer, then this will be lost. Like if this is my subroutine, and there somewhere I change the stack pointer value, so LXI SP to something else, and then I put a return, then what will happen? So, it will be trying to load this stack, it will load the stack pointer with something else. So, when the return is executed, so it will try to get the return addresses from that other location, not the location where the this return address was saved while the call instruction was being executed. So, we should not modify the stack pointer in a subroutine, otherwise we will lose the return address value. So, that we have to be careful. So, you can also use this stack to pass data to a subroutine. So, in assembly language program, so we can pass data to a subroutine through registers. So, that is one possibility. So, this data is stored in one of the registers by calling the program, and the subroutine uses the value from the register. So, by the calling program, what, for example, if it has to pass an 8-bit value, it may be that it saves the value in the B register and then calls the subroutine, and in the subroutine we access the B register to get the value that has been passed. So, that is one possibility. So, you can use one register to hold some parameter that you want to pass to the subroutine. But since the number of registers are limited and they are also used for some other purposes, so it is better that we have some option. Okay. So, and that option is via the stack. Okay. So, if because memory is very large compared to the data the space requirement of a program for the data space requirement of a program. So, we can use this stack for the purpose of this transfer of these parameters. So, what the program does, the calling program, instead of storing the content of this data onto a register, it can store the content in a memory location, and the subroutine will retrieve the data from the location and use it. So, that is possible. So, that way we can have some memory location and to do that operation. Now, if the subroutine performs operations on the contents of the register, and then these modifications will be transferred back to the calling program upon returning from the subroutine. So, this is called call by reference, and if this is not desired, then subroutine should push all the registers it needs on the stack on entry and pop them on return. So, this is the original values will not be lost. So, what we mean is like this, that suppose I have a subroutine. Okay. So, I have a subroutine where so this is my subroutine, and there I am using these registers, like this part of the code I am using the registers B, C, H and L. Fine. Now, what can happen when these modifications are done? So, this is so if this is the main program from where I am calling this subroutine. So, there is a call instruction here which actually calls this subroutine, and somewhere here I have got the return. So, it will be coming back to this point. Now, if this subroutine modifies these B, C, H, L registers, then once you come back here, you see that B, C, H, L are all modified. So, whatever be the values of these B, C, H, L registers here, so they are modified by the subroutine. Okay. So, if you want that, so there may be situations in which you want it. So, maybe it is doing some computation in the B, C, H, L register values in the registers, and then those values are needed by the calling program. So, that is one possibility. Other possibility is that this BCHL, so they were used as some temporary storage by the calling by this subroutine, and the values of those registers on the original program, they should not be modified. So, for that purpose, so we have got two type of situation. One is call by value, another is call by reference. So, in case of call by value, the original registers should not be affected. Original registers should not be affected. So, this is the situation I was talking in the second case, that is whatever be the values of BCHL here, so that should not get disturbed. And call by reference means original registers should be affected. They should be affected. Now, the second part, the call by reference implementation is very simple. So, you do not have to take any precaution to restore the values of BCHL, but if you really want that this BCHL content should not be lost, you have to have a call by value. Then the first few instructions of this subroutine, it should be push B and push H. So, they will be saving those two registers, and before doing this return instruction, okay, so I should pop them out. So, I should use instruction like pop H and pop B before the return, so that the values are restored. So, the original content of BCHL registers, so they are not lost. So, this way we can do this call by value and call by reference type of implementation by using the stack. So, if the subroutine performs the contents of the registers, then these modifications will be transferred back to the they will be transferred back to the calling program upon returning from the subroutine. So, this is the call by reference, and if this is not desired, then the subroutine should push all the registers it needs onto the stack on entry and pop them on return. So, this is the original values are restored before execution returns to the calling program. So, that has to be done. Now, push and pop, as we have already said that the push and pop should be used in the opposite order. The order in which you push the registers, you should pop in the reverse order, and there has to be as many pops as there are push. Okay, so, if the number of suppose for example, when this say the number of push is say 4 and number of pops is 3, that means the situation is like this, that when you are calling a subroutine, you know that so first the return address is saved onto the stack. So, PC high and PC low. So, if we draw in terms of a stack, so it is like this. First the PC high will be stored, then the PC low will be stored, and then if you say that I have pushed these registers B and C, then the B register will be saved here, then the C register will be saved here. Then if I push say D and E, then E register will be saved here and D register will be saved, sorry, D register will be saved here and E register will be saved here. Now, while doing the pop, so naturally when you are returning, so it is desirable that when you are returning the stack, everything has been erased from the stack and the stack has got this PCL and PC high at the two topmost entries. So, if there is a mismatch in the number of pops, push and pops, like if you, maybe I have just popped out these two by using a pop instruction and I did not do any further pop. So, the stack top actually contains the register values B and C, the old values of B and C. Now, if you do a return now, then the C register value will go to PC low and the B register value will go to PC high, and that is dangerous. So, it will take your program to somewhere else, not to the point from where the subroutine was called. So, this RET instruction statement will pick up the wrong information from the top of the stack and the program will fail. And it is not advisable to put this push and pop inside a loop, because it is often very difficult to judge like how many pushes or pops will be done and whether they are really balanced or not, because the last iteration of the push pop, last iteration of a loop, so normally it comes out without executing the body. So, in those cases it is difficult to ensure that this push pop they will be matching. So, if you try to put this push and pop instructions outside the loop, and if it is very much necessary to put inside the loop body, then ensure that it is put at the beginning of the body and popped out at the end of the body, and ensure, and they are always executed. So, it is not that in some cases the pop may not be executed, it should not happen like that. So, that way we have to be careful with this push and pop instructions while writing the subroutines.